Exploring with the Estuarium. My name is Aeriel and I'll be your educator. Today we're going to learn all about ocean density and what happens when the river meets the sea.
During the estuary density lesson, you'll learn how to answer how is salinity different in the estuary compared to the open ocean, what determines density of seawater, how does density affect the estuary, and why is the Puget Sound so productive? Before we learn about density, we first have to understand salinity. What is salinity? Salinity is the concentration of dissolved salt in a given volume of water. Salinity is either expressed in grams of salt per kilogram of water or in parts per thousand, ppt. For example, if you have 1 gram of salt and 1,000 grams of water, your salinity is 1 gram per kilograms, or 1 ppt. During high tide, the salt water is driven far up into the estuary. This occurs twice in a 24-hour period here in the Pacific Northwest. By contrast, fresh water dominates the estuary during low tide. Salinity in the estuary is the result of a constant battle between the fresh water from rivers and streams trying to dilute the salt water of the sea. High tide gives the advantage to the sea, while low tide provides an advantage to the fresh water. Different salinities can be expected in different areas of the estuary depending on the seasons of the year. Ocean water is a combination of fresh water and a variety of dissolved ions of salt and other trace elements. While local differences in salinity and temperature of ocean water occur, the composition of seawater is uniform around the globe and has been for a major period of geological time. When we measure the amount of dissolved salts in seawater, typically seawater has a salinity of 35 parts per thousand. The Puget Sound has a much lower salinity level, about 20 parts per thousand, due to about 10,000 rivers and streams of fresh water flowing into it every day. Variations in salinity can be measured through conductivity, or the ability to conduct an electrical current, evaporation, the refraction of light, or using a simple hydrometer. If we took water from a freshwater stream, the Puget Sound, and the Pacific Ocean, which would have the most salt content? And which would have the least salt content? Yes, the ocean would have the most, and the freshwater stream would have the least, and the estuary water would be in the middle. Remember, an estuary is where fresh water and salt water mix. We usually measure salinity in parts per thousand, which is the grams of salt in 1,000 grams of solution. If there is 1 gram of salt in 999 grams of water, there is 1 gram of salt in 1,000 grams of solution, or 1 parts per thousand of salt. If there is 2 grams of salt in 998 grams of water, there is 2 grams of salt in 1,000 grams of solution, or 2 parts per thousand. To find salinity, simply subtract the amount of grams of salt from 1,000. Now let's think of salinity in the terms of sprinkles and rice. Sprinkles represent the salt, and the rice represents the water. If we have 1 sprinkle per 999 grains of rice, our parts per thousand would be 1. If we had 35 sprinkles per 965 grains of rice, what would the salinity be? 35 parts per thousand. 0.5 parts per thousand is the limit for drinking water. 1 parts per thousand would likely make you sick. Our freshwater streams are anywhere from a 0 to 0.5 parts per thousand salt. The Puget Sound sits anywhere between a 20 to a 28 parts per thousand, and the ocean is around 35 parts per thousand. Now that we've learned about salinity, we can better understand density. Density is the mass of a substance in a given volume of that substance. Saltwater is denser than freshwater, so it tends to sink to the bottom. There is often a distinct layer of freshwater floating above the saltwater. We call that stratification. Wind, waves, and tides can stir up the layers, so the estuary animals and plants need to be prepared for quick changes in salinity. Typically, seawater has a salinity of 35 parts per thousand and a density between 1.026 and 1.028 grams per milliliter. Ocean currents are large-scale water movements that occur at the surface and in the depths of the ocean. Surface currents are driven primarily by global wind patterns, while subsurface currents are driven by ocean water density differences. Subsurface currents may also be caused by differences in the salinity or by the temperature variations. As very saline or cold water sinks, the less saline or warmer water is displaced and rises to the surface. Stratification of water throughout the ocean water column is formed, where circulation varies depending on the location, temperature, and salinity of the ocean water. Changes in density contribute to vertical mixing. Upwellings bring nutrient-rich water to the surface. The nutrients help support very productive food chains. The Puget Sound has a unique shape. Much of the sound is very deep. The deepest spot is almost 950 feet off Point Jefferson. The Puget Sound is very deep because it was carved out by glaciers. Glaciers pushed around piles of rock and soil. Some of the rock and soil is left on the bottom of the sound, which are called sills. There are 3 major sills in the Puget Sound: Admiralty Inlet, Tacoma Narrows, and Hood Canal Mouth. When the tide rises in the sound, the water comes from the Pacific Ocean. When the tide falls, the water goes back to the Pacific Ocean. The difference between highest and lowest tides in the Puget Sound often goes well above 10 feet, sometimes 15 feet. Lots of water must pass through narrow channels, which creates fast currents. Most of the water flowing in from the ocean rushes right in, but the deep water goes up. This upward mixing of deep water into the surface layer and upwelling helps phytoplankton by bringing nutrients up at all 3 sill locations. Phytoplankton in the sound keep growing through spring, summer, and early fall, and that's why the Puget Sound supports such an abundance and variety of animals. Now we're going to do a little hands-on activity that demonstrates what happens when the freshwater and saltwater meet along with upwelling. You can follow along by using our student activity sheet. You'll need 1 container with a divider or a partition, 2 large glasses of fresh water and 1 of salt water. You can make your own salt water by adding 35 grams of salt to 1 liter of fresh water, a stirring spoon, 2 different colors of food coloring, and color pencils that match your food coloring. First, we are going to dye our water to indicate which one is fresh and which one is salt. I am going to now dye the salt water with blue food coloring. I'm going to add about 2 squirts of food coloring. And then we're going to use our stirring rod or spoon to mix in the color. If you're following along on the student activity sheet, please mark your salt water as the color you have dyed it. Now we have to dye our fresh water, so adding 2 squirts of the food coloring into the freshwater container and stirring it all together. If you're following on the student worksheet, please label your fresh water with the color you just dyed it. We are going to pour our salt water into one side of the partitioned container. Make sure your partition is sealed tightly so there are no leaks. And we will fill the other side of the partition container with our fresh water. Please mark on your student worksheet in number 1 which side of the containers your fresh water and your salt water are. Now that we have both our salt water and fresh water inside our density flow model, we need to make a prediction on what visible changes will be observed when the partition is removed between the fresh water and the salt water. Will the fresh water and salt water stay separated? Will they end up mixing? Or will they become layers? Please take this time to draw in your predictions for question number 3 on the student activity sheet. Watch what happens when I remove the partition. So what happened after 3 seconds? What happened after 30 seconds? Was your hypothesis correct? If you said that the water would stay separated, you're partially correct. If you said there would be mixing, you're also correct. and if you said they would layer, you are correct again. Due to the saltwater's heavier density, it flowed to the bottom, and due to the freshwater's lighter density, it flowed to the top. When we opened up that partition, there was a little bit of upwelling, which mixed both the freshwater and saltwater, causing that middle layer. So we have a blue layer of saltwater on the bottom, a mix of fresh and saltwater in the middle, green, and we have our freshwater sitting on top in the yellow. You've just watched density in action. Don't forget to fill out your answers for number 4 and 5 on your student activity sheet.
Thanks for joining us today on another episode of Exploring with the Estuarium. If you liked our video, please give us a thumbs up. And if you wish to continue to get more of our educational videos, please subscribe to our YouTube channel or follow us on Facebook at the Puget Sound Estuarium. Bye!